Okay, thank you very much, Laurentio. So let me give you some overview and the summary of our now 10-year-old work with Nima Akani Ahmed on the amplituhedron, and what it means and how is it defined. And in the end of the it will be very impressionistic, so some formulas, but not so many, just to get some main idea out. And then in the end of the talk, I will mention some more recent work about what actually has been done in the last few years and how to use this picture to get some explicit calculations. Okay, so the general question we would like to address here is how to define and possibly calculate the perturbative S matrix in quantum field theory. It's a very broad question. The standard answer that we can find in the textbooks is that we draw Feynman diagrams, we sum all of the contributing ones, and we get the S matrix, this in the perturbation theory. But yeah, I will show that at least in a very special case, but by now there are more examples of the same phenomenon, despite not a general approach how to do it for arbitrary quantum field theory. There is a different definition of what the amplitude is, and it's not referring to some expansion like Feynman diagrams, but it has an intrinsic definition as a mathematical object which looks very different from our physics intuition. Okay, but let me just mention how it fits into a larger scheme or a larger field of scattering amplitudes, which is now a very wide field, which ranges from developments in the formal theory to collider physics and now also gravitational physics. And people are doing different type of work depending on their interest and the motivation. So in my case, I will focus on this corner here, and it's about exploring new theoretical methods in simplified quantum field theories. So we don't have an ambition at the moment to apply it to relevant collider physics, but you like to explore new methods with potentially generalizing them to broader set of theories and learning some more general lessons for quantum field theory. So let me start with the scattering amplitude. So in the theoretical predictions for the scattering of elementary particles, we define an amplitude, which is a mathematical function, which depends on energies, momenta, spin structures, information about the particles. And this mathematical function is then used to calculate the cross-section, which is something which then can be measured for realistic theories at particle colliders. Now, in our case, we stick to the weak coupling expansion. So we have to assume that the coupling is weak, and we can use perturbation theory to calculate our scattering amplitude. And the perturbation theory is an expansion in a coupling, and already in the early days of quantum field theory, the Feynman and then Schwinger taught us how to calculate scattering amplitudes, that we should expand in coupling, and each term order by order in the perturbation theory is given by a sum of 3 diagrams, 1-loop diagrams, 2-loop diagrams, 3-loop diagrams, and so on. Of course, this perturbative series is typically not convergent. It's an asymptotic series. There are non-perturbative effects in most of the theories that if you would like to do something precisely, you have to deal with. Now, the Feynman diagrams provide a diagrammatic organization of the terms in the perturbation theory, and this is how most amplitudes have been traditionally calculated. Now, for us, the main object of interest, we will be not very broad, will be amplitudes in QCD, and then later we will also narrow it down to some supersymmetric version of the QCD. But let's first talk about just QCD. So QCD, as a part of the standard model theory for strong interactions, has quarks and gluons as particles that it describes. At low energies, they of course are hidden in hadrons due to confinement. But at very high energies, we can treat these particles and free, and it makes sense to talk about scattering of gluons, scattering of quarks. Now, from the theoretical perspective, the most complicated and most interesting, the most complex part of these processes are gluonic amplitudes, because the way how the gluons interact. there is a huge number, very complex, huge number of Feynman diagrams that contribute to a given scattering process of gluons. So that has been challenged for a long time, how to calculate these gluon amplitudes efficiently. And the standard procedure, again, given by Feynman, is just to draw all possible Feynman diagrams. At tree level, it's really just gluonic amplitudes with no exchanges of quarks. Sum all of these diagrams and get the amplitude for a gluonic scattering. And this wasn't just a completely theoretical exercise. In late 1970s, people did the first kind of non-trivial calculation, which is 2 gluons going to 3, which we will call 5-point amplitude, and at 3 levels, so at this leading order in the perturbation theory. And even this calculation is already, using the traditional Feynman diagram method, very complicated. And once you just do straightforwardly the calculation, you end up with 24 pages of algebra like this. This is one of the pages when these small things are some scalar products of polarization vectors and momenta for particles involved in the process. Now, the history kind of here touches very strongly experimental physics, because the superconducting supercollider was approved in 1983 to be built in Texas in the United States. And there was a demand for theorists to provide more precise calculations for these gluonic amplitudes as a QCD background for the collisions that would have been seen there. And the energy of the SSC was supposed to hit 40 TeV, so that would mean higher orders and higher multiplicities of amplitudes needed for the accurate prediction of the background. Of course, if SSC was built, which never was, we would see Higgs probably in early 90s, so in late 90s. This didn't happen, but the calculations, which were motivated by the SSC, did happen. And the next in the line, apart from this one, which was done in 1970s, was a 6 gluon amplitude, 2 gluons in the initial state, 4 gluons in the final state. And this calculation was completed in 1984 by Stephen Park and Thomas Taylor. And again, Feynman diagrams were used. 220 Feynman diagrams contribute to this given process, and the result is roughly 100 pages of algebra, like here. Now, Park and Taylor, once they finished the calculation, they used supercomputers back in 1984, compressed the result into 14 pages, which can be printed in the paper. And the paper they wrote is called just gluonic 2 goes to 4, and in the abstract of the paper, they write that the cross-section, the square of the amplitude, in their case, for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculations. So their motivation is not really to put this result out, except for experimentalists to use it for QCD background calculations. Now, this is the paper. These are the 14 pages. There are some kinematical terms. There are some tables with coefficients. They wrote like expanded the result in bases. There are many symmetry factors and so on. So they compress it as much as they could in these 14 pages. And then in the conclusion of the paper, they also write that furthermore, we hope to obtain a simple analytic form of the answer, making our result not only an experimentalist, but also a theorist delight. So they probably hoped that there is some simplification to this answer. And they were right, because within a year, they realized that the square of the amplitude that they wrote could be written as a single line formula. So there was a huge simplification, which was completely invisible in the standard way how to do the calculations. And it pointed to some underlying structure, not visible at that time. Furthermore, in a year, they also noticed that this formula generalizes. If you just look at the formula and the way how it's structured, these are the scalar products of momenta, you can guess what is the endpoint generalization. And this is what is known called as MHV formula. And it's a 3-level amplitudes of gluons for specific helicities. So it's not a completely general, but for one specific helicity, you can write a 1-line formula for n gluon scattering, arbitrary number of points, which would require, in principle, infinite number of Feynman diagrams to sum. Okay, so following this discovery by Park and Taylor, people started to wonder if there are other ways how to calculate scattering amplitudes, not just using Feynman diagrams. Of course, Feynman diagrams have been very successful, very general. You can use it in any theory. Complete prescription how to do calculations. But as was seen in this calculation by Park and Taylor, and then other calculations afterwards, they often hide some underlying simplification, underlying structure of the amplitude. Now, there was another method called analytic S-matrix program, which was predated QCD and basically died after the QCD was developed, which was very ambitious and basically was not successful, failed back then in 1960s. And the idea was that you should treat the amplitude, the S-matrix, as a mathematical function, and you should find enough constraints to fully fix it. And the ambition of people back then was really to fix full non-perturbative amplitude, which was extremely ambitious thing. We don't know how to do it at all by now. But the idea of fixing the function using some mathematical properties is actually very important from everything what followed. For most of the modern methods for amplitudes kind of combine both of these sides. Combine Feynman diagrams in a sense of perturbation theory. So things are simple in perturbation theory. We should follow that. But at the same time, we would like to treat the individual amplitudes order by order in perturbation theory as something we would like to fix using certain conditions, and then find a method which would reconstruct it explicitly to calculate. And there are many methods depending on what exactly you want that have been developed, including generalized unitarity by Dixon and Kosover, recursion relations, which I will briefly mention, different string-based methods, and yeah, by now we have a whole menu of different approaches to scattering amplitudes, which typically work only in certain situations. Some methods are very general, like these recursion relations, which work for tree-level amplitudes, or generalized unitarity. Some methods are really tailored to the problem that you are interested in. Now, let me mention a little bit these tree-level amplitudes just to see how efficient they are. So the most famous version is BCFW recursion relation by Brito, Jaroslav, Trnka, and Whitman from 2005. So relatively recently, considering how simple the idea is. But the technical implementation took many years to actually realize how to do it. And the idea is that instead of calculating the endpoint amplitude from scratch, you should recurse from lower point amplitude. So once you already have everything up to n-1, there should be just minimal amount of work that you do to push it to endpoint. And if you use these recursion relations, which work pretty broadly for not just for gluon amplitudes, but for many other theories, the number, so here is a comparison of number of terms, Feynman diagrams contributing to different tree-level processes and the number of terms in the recursion. And this is the kind of state of the art, or this is the most efficient way how we know how to calculate these amplitudes. Later on, we also found, with my collaborators, we found a specific version of these recursion or implementation of these recursion in some more mathematical structures called on-shell diagrams, positive Grassmannian, which I will also shortly review, which kind of extract the most invariant information for each term in the recursion. And it turns out to be that the most invariant information that you need to do to reconstruct these expansions are just set of permutations. So if you give me permutation, it basically defines one term in the recursion, and you can write easy mathematical code, which turns it into formulas. So this set of 6 permutations here basically is the information which is enough to write a 7-point amplitude of gluons, which would be normally something like 2500 Feynman diagrams. Okay, this was for trees. The recursion relations work for trees. There are some attempts to extend them for loops, as well as other methods. But the loop amplitudes are more complicated. Tree-level amplitudes are rational functions of kinematics, and rational functions are nice. We can calculate residues. But loop amplitudes are transcendental functions, and actually the space of functions that you get at loop level, we don't even know. And we don't know even at beyond two loops. Or certain degree, we know what happens at two loops, but it's kind of very uncharted territory, despite in a different direction in the scattering amplitude field, people calculate loop amplitudes for practical purposes. So there are a lot of data, but the mathematics behind them seems very complicated at the moment. Now, so instead of calculating loop amplitudes, in our case, and in other cases when people develop new methods, we simplify our life. And instead of calculating this, what we really want, which is some complicated function, and also it's typically divergent, both UV and IR, so we have to also treat that. We do something simpler, and we calculate a rational function called loop integrand, which is a function we are supposed to integrate over the loop momenta to get the actual amplitude. Yeah. So the integrand is a very useful concept, despite it looks like some intermediate thing that you are supposed to integrate it, but it turns out to be very rigid object. In more special quantum field theories, it's even unique. Yeah. And then you can calculate this object, and these unitarity methods is one way how to calculate it, expanding in some basis of integrals, which you know, and calculating their coefficients, the cuts. So this is how people do it on very general grounds. But in our case, we will also calculate this integrand using very different methods. Yeah, but I just want to mention here this difference between loop amplitudes, what we actually want, but these are complicated functions, and the loop integrand, which is a rational function on the right-hand side of this equation. Now I narrow down from QCD to more special theory. Because in order to make progress, we have to start with something simpler. And this theory is called planar n=4 super-Young-Mills. And this is our favorite toy model for four-dimensional interacting gauge theories. And it has been a very useful playground for many theoretical ideas in the last 25 years. This theory has a maximal supersymmetry in 4 dimensions. It's UV finite, so the superpartners to gluons cause cancellations of all UV divergences. It's a finite theory. Because of the infinite number of colors, that's what the planar limit corresponds to, the number of colors is infinite, only planar diagrams contribute. So we even simplify kind of the topology of Feynman diagrams we would potentially get, or not just Feynman diagrams, also these terms in the unitarity method, only planar things contribute. And so that simplifies things a lot, and it has a profound consequences to using labels on these diagrams and so on. And this theory also, apart from amplitudes, was also very important in the ADS-CFT correspondence, because it's a theory which is dual to supergravity theory on the other side. Now, what do we lose? Well, of course, we lose the properties of QCD, like confinement and the fact that we have to deal with the UV physics, which we don't have to deal with here. Yeah, this is all about IR. The IR physics of n=4 super-Young-Mills, it's pretty complicated, and it's a little different than QCD, but it's not much different, while the UV is completely different. This is a UV finite theory. Yeah, and there is no confinement, so it's defined at all energies. It's a conformal theory. Now, why is it still a good toy model? Well, there are several indications. Well, first, the 3-level amplitudes of gluons are the same as in QCD. So once we calculate them here in this theory, we get immediately the amplitudes of gluons in QCD, because at 3 level, the superpartners don't propagate. So the difference between QCD and n=4 is just some level, it's a matter of some bookkeeping. There is no principal difference. They are the same. The amplitudes are simpler, the loop amplitudes in this theory, of course. But there are some, you can think about the n=4 part as one piece in the QCD amplitude, and there are more pieces. So we are not calculating everything, but we calculate one piece of the answer if you want to refer it to QCD. Now, there is a big advantage here if you would like to play some game with resummation to all loop orders, which we potentially would like to do. because the perturbative series in any planar n=4 superangles, it's actually convergent. It's not asymptotic like in most other theories, but it's convergent. So if we can handle the amplitudes to all loop orders, we can actually resum them and learn something about non-perturbative. Well, there are no non-perturbative corrections, but we can give some exact statements and look at the strong coupling, for example, which we will do here in the end as well. And now there is a more practical reason that the past experience says that it's always good to develop new methods in the toy model, especially this toy model for amplitudes, and then extend it to others. It's more aspirational that we would be able to extend it eventually, but it worked in the past for a number of examples. Okay, so now let me for a bit kind of almost completely switch the gears and start to talk about something completely different, but it will quickly become relevant for amplitudes, and this is how the amplitude will be defined. So let's completely switch the gears and just talk about one mathematical object called Grassmannian, GKN. And this is a configuration of k-planes in n dimensions. So we have a k-plane in some n-dimensional space. So we can describe it by some k by n matrix modulo GLK, modulo the choice of the basis on this plane. And there is a restriction on Grassmannian called positive Grassmannian. So if all the entries here are real, we can say that we demand that all the ordered minors of this matrix are positive or non-negative. Okay, and this is called positive Grassmannian. So it's some space with boundaries. The boundaries corresponds to sending some minors to 0. And yeah, it's an interesting space. It's been studied in mathematics in the last 20 years. Has many interesting properties. It's topologically a ball. It's related to algebraic geometry, combinatorics. And it happened to be relevant for amplitudes. Now, the point when it's related to amplitudes is through objects called Plaby graphs. We call them on-shell diagrams in amplitude. But they were first seen in the mathematics. And each graph represents one of these C matrices here. So there is a way how to build this matrix, which is actually very complicated. Yeah, I give you a matrix with a bunch of numbers, it's very hard to choose variables such that all the minors are positive. Or yeah, if you just put some random numbers, you calculate the minors, some of them will be definitely negative. Yeah. So the mathematicians thought about this problem, how to find a parametrization of a real matrix where all the ordered minors are positive, and they came with the answer to that. And this is that you draw these graphs, these Plaby graphs, which are trivalent graphs with two types of vertices, white and blue, and black. And using the graph, which corresponds to the matrix, you find variables which will then parameterize the matrix such that all the main minors are positive. So this was started by Gelfand McPherson in 1984 for some simple example of 2x4 matrix and this graph, and then generalized by Posnikov in 2006 to any GKN. So there is a way how to start with this graph, choose some variables on the graph, and then there are some rules how to parameterize this matrix using the variables of the graph. Yeah. It's called perfect orientation using edge variables. There are some procedure how to do it. Okay, so this seems like a problem in math, how to parameterize these positive Grassmannians. But there is a connection to physics. So first, the same graphs, these Plaby graphs, appears in physics as on-shell diagrams, and they have several purposes, several meanings in physics. One of them is that they correspond to cuts of loop amplitudes. So this diagram is certain cut of two-loop 5-point amplitude that you see. It's when you set the propagators to be on shell in the two-loop 5-point amplitudes. The internal lines are on shell here. And at the same time, they also serve as building blocks for trees in these BCFW recursion relations. So there are new building blocks for amplitudes used for different purposes, but they serve as building blocks. And The k and n in the mathematics, which corresponds to the size of this matrix, corresponds to the number of external particles, and the k is some helicity number of negative helicity gluons. The rest are positive helicity gluons in amplitudes. But so far there is no connection. It's just the same object used in physics and in mathematics for different purposes. One calculates a matrix, the other one is used for amplitudes. Now the connection is that the result in physics that you get from gluing together 3-point amplitudes in these corners, this is what is done in these unitarity methods, and getting some result in terms of kinematical variables, here written in terms of spinor helicity variables for massless particles in 4D. The same result can be obtained from the mathematical side using this C matrix and writing some simple differential form on this positive Grassmannian, and then relate the variables of the C matrix to kinematical variables on the other side of physics. Yeah, so there is a completely dual prescription here on the right-hand side, how to calculate these objects in amplitudes on the left-hand side. Okay, and still here there is this connection between both sides. However, as I said, these objects in physics are only building blocks for the amplitude. So we can write the 3-level amplitudes and also put these loop integrands that I was talking about as sums of these objects. It's like a sum of Feynman diagrams, but now instead of Feynman diagrams, we have a new types of objects, these on-shell diagrams, which have very nice properties. They are gauge invariant, on-shell, so on. They preserve some hidden symmetries of this planar n equals 4 super-Yang-Mills theory, but the amplitude is still a sum of many objects. Now, there is a way how to glue them together into a simple object, and that's what the amplituhedron is. So using this intuition, these on-shell diagrams play big role from mathematics, using the right set of mathematical tools, you can identify that the full amplitude at 3-level and for these loop integrands can be written as certain volume, more precisely some differential form with logarithmic singularities on the boundaries of some region, and that's the amplituhedron region. And now if you break it into pieces, you triangulate this geometry, you reconstruct, or you get an expansion of the amplitude using, for example, these on-shell diagrams, recursion relations, or Feynman diagrams. Feynman diagrams, you have to break it into many, many pieces. It's like a very inefficient way how to triangulate geometries, but it's a possible way. Yeah, so it's also legit triangulation. Yeah. Here, geometrically, it's easy to see why these recursion relations are very efficient, because it's the most efficient way how to break the geometry into pieces. But in principle, there are different ways how to express the amplitude. But the amplitude itself is a single object and corresponds to this differential form on this one region in this amplituhedron space. And now in this way, how to think about the scattering, there is kind of no dynamics of particle scattering. So all the information about the gluons, how they interact, and so on is gone. There is some static geometry, and the only thing that it remembers from the particles are the kind of positions of these vertices, which are given by some kinematical data, and the way how they are joined together. So, so there is a complete translation of the physics into these geometric data. Okay, so that was kind of a overview. And now let me give you a little bit more flavor of what exactly this object is. So like historically, everything started in 2009 by Andrew Hodges, who realized for the first time this idea that amplitude can be volume. So he tried to understand some properties of the scattering amplitudes in momentum twistor space. This is just some kinematical space which is used in planar theories. And in the end, the details are not that important, but for each particle, we have just some vector z, which is a vector in projective space D3, instead of talking about momenta. The problem with momenta is that they satisfy momentum conservation. This is the way how to trivialize momentum conservation. Now, doing calculations using these DCFW recursion relations, for some simple 6-point process, not the one calculated by Park and Taylor, that was too simple, but the one when you have 3 positive and 3 negative helicidal gluons. This is some graphical way how to represent these recursion relations. He associated with them the formulas when you just translate from momentum space to this momentum vector space. These brackets are 4x4 determinants of these z vectors for each variable. So these are the formulas that you get, and he realized that the formulas correspond to volumes of tetrahedra in this momentum vector space. Something that he saw already before because he studied volumes in this vector space, and this is what happened for the scattering amplitudes for this particular process. Now, interestingly, the things that are in the denominator of these formulas corresponds to faces of this tetrahedra. The tetrahedron has 4 faces, and one of the face, when you glue these two things together, is spurious. So once you glue them together into the polyhedron, that face disappears, and that's exactly what you saw. It's a spurious pole in the amplitude corresponding to the spurious space in the geometry. So the amplitude is a volume of this particular polyhedron in this case. And these recursion relations was one way how to triangulate. So there was this general idea since then that amplitudes are volumes of some region in some space. But his original idea didn't generalize to anything beyond here. But the generalization to the Grassmannian eventually led to the amplituhedron, generalize it to all 3-level amplitudes and also these loop integrants. So to see what the amplituhedron is, let's start with the simplest example, which is a triangle in a plane. So the triangle in the plane, we have 3 points, and we would like to describe the point inside this triangle. So each of these z's is like a momenta of particles. So these are like 3 particles. This is a toy model, so it doesn't actually correspond to any real scattering. And the point inside this triangle can be described as a linear combination of these points z's. In order to put the point inside and not outside, the coefficients in front of these z1, z2, and z3 must be positive. So if they are all positive, the point y is inside. So the way how to describe triangle, the simple way is like this. Now, because this is a projective space, not a real space, we can fix one of these coefficients to 1, because there is some projectivity. So there are really only 2 parameters. It's a 2-dimensional space. Now, if we want to access a boundary, to move the y to a boundary, we have to send one of these coefficients to 0. So being on this boundary means that y is a linear combination of 1 and 2. It means that it's somewhere on a line 1 and 2. Accessing this boundary sets another coefficients to 0, this boundary, like that. And if we want to go directly to a vertex of this triangle, we have to send 2 of the c's to 0. And then y is directly z1. Projectively, it is the same point. Okay, so if we fix this projectivity, we can write y as a sum of these 3, z1 plus z2 plus z3, with some coefficients here. And in order to span all the triangle, we just have to vary the c2 and c3 from 0 to infinity. And now, so this was interior of the triangle. And now we would like to associate a form with logarithmic singularities on the boundaries. So whenever we hit the boundary, the form blows up as dx over x, as a logarithmic singularity. And in this parametrization, the form is just this, but we can unparameterize the whole thing using just these projective variables, z1, z2, z3, and point y, and write it in this form. Yeah, so this is a projective way how to write this logarithmic form. So this is a form with logarithmic singularities on the boundaries of the triangle. And it's the form in this point y, which is inside triangle. We can do it for polygon as well. Now, in order to be inside polygon, you have to take y and express it as a linear combination of all vertices. Now, this must be a convex polygon for us. And if all the parameters are positive, then you are inside. However, that's too many parameters. This is still 2-dimensional geometry. And we don't have so many degrees of freedom of this y. Yeah, so there is a condition in order the polygon to be convex. If you build a matrix of all these z's corresponding to vertices, the matrix must have positive minors. If there's positive minors or ordered minors, then it's convex. Okay, so the generalization then of being inside a triangle to going inside a polygon is writing it like this, and we can more formally write it as a matrix multiplication of the C matrix, which is just an arrow of coefficients which are all positive, and the 3 by n matrix, which is a collection of these points in the vertices of the polygon. And this row of positive numbers is also a first example of a positive Grassmannian. In this case, just very trivial, G plus 1n. It's a 1 by n matrix with all 1 by 1 minus positive, which means that the entries are positive. Now, in order to find the differential form, we have to triangulate. So we have to divide the polygon into triangles. And then we write a differential form for each triangle separately that we already know how to do from the previous example. And we sum them all together. Sum all the forms corresponding to triangles. Now, so this is a perfectly good way how to write the form. But know that there are, again, these spurious boundaries from triangulating. So some of the poles in the form corresponds to spurious boundaries. And these are spurious poles in the form. And once we sum everything together, they should cancel, because the only boundaries are really just lines I plus 1, zi plus 1, which should show up in the denominator of this form with some non-trivial numerator. So this is the right result, but the only way how in principle we know how to calculate this form is to break it into triangles. The form for each triangle is simple, and then sum them together. Once we have this form, so there is some idea how to go directly to this form as well, from the numerator canceling certain singularities in the denominator, like a singularity at this point, which is outside of the polygon. Now, once we already calculated this form, going to the amplitude is simple. There is some straightforward operation, how to turn this into something which already has kinematical data of gluons. This case actually doesn't correspond to amplitudes. It's a toy model, but a straightforward generalization of this case, which is not a polygon in P2, but some polyhedron in P4, actually corresponds to the first case of scattering amplitudes. So once you calculate this D-log form for that, you can directly go to the 3-level amplitude on the other side. This is already representing some 3-level amplitude. Okay, just the boundaries here change. Instead of being the lines, these are 3-dimensional planes. Now we are in higher dimensions. Now the amplituhedron is just, in the general case, is just direct generalization of the mathematics behind these polygons. So we started with a polygon, point inside a polygon as this multiplication, matrix multiplication C dot Z, where C was this this row of positive numbers. Z was a matrix with also positive minors. So this was for polygon. If we now replace, we keep the same formula, but we replace the C by a matrix K by M, the positive Grassmannian in a K by M, and we also increase the dimensionality of the Z to properly match it, then we get 3-level amplitude in the planar equals 4 superangles. So this is a 3-level amplituhedron. There is some extra parameter M, which you can keep in math, but in physics, this corresponds to number of space-time dimensions, which must be 4. And there is also generalizations to loops. So for the loop integrand, in addition to kind of the 3 parts that we have here, we have also the loop part corresponding to loop momenta. They also enter this geometry. So enter the geometric data, represent the degrees of freedom in the loop momenta. And there are certain conditions, again, positivity conditions of matrix multiplication, which defines the geometry. Okay, so that gives the 3-level amplitudes here, and the loop integrand in planar n equals 4 superangles. So this is the definition of the space. So the amplituhedron in this case provides a new mathematical definition of what the object is. It's a differential form on certain geometry, and the geometry is well defined. Now, the challenge here is to, of course, calculate the amplitude, which requires to determine what the differential form is. And In general, this is a complicated problem in mathematics to calculate volume on differential form for some arbitrary geometry like this amplituhedron is. The general way how to do it is to triangulate. So once you triangulate a space, like we saw for the polygon, in terms of some simplicity, some simple objects when the form is trivial, then we just sum them and we get the differential form for the whole space. So the mathematical question here boils down to the triangulation. How do you triangulate a space? And this problem hasn't been solved with the amplituhedron. Amplituhedron happens to be very complicated mathematical space, but in recent several years, a lot of pure mathematicians have been studying this object, but so far mostly for the tree-level case, when we as physicists know how to calculate tree-level amplitudes. We don't know how to do it for loops, but we hope that the mathematics will catch up there. They provide us with some important insights how to do this calculation. Okay, so let me just say what the problem here is. So we do have the definition of the geometry. It's some space defined by inequalities in some parametrization, which parameterize these kinematical variables. And once we triangulate it, we would like to calculate the differential form on this space, and that would be an amplitude. So the only way how we know is to triangulate it into simple pieces when the differential form is trivial. But the triangulation itself means that we have to divide this region into a set of non-overlapping regions when there are no the variables that cover these small regions just run from 0 to infinity, because then we can write trivially the form, and then we have to sum them. Yeah. So of course the setup is clear, but how to do it for these geometries is difficult. So to give you one example, let me show what the amplituhedron gives. What is the mathematical problem in which it is translated? The problem of calculating 4-point scattering to all loop orders. So this is something that in Feynman diagrams or unitarity methods would require just draw all diagrams to arbitrary loops and sum them. So this is not very well defined problem. Here in the geometry, we just reduce everything to a space defined by certain inequalities. Yeah, so if we have only one loop, we are talking about one line in some three-dimensional space, which is parameterized by 4 parameters as x, y, w, z. Yeah, let's suppress the details here. And the space is just a space of x, y, z, w is positive. This is a very simple space. Yeah, it's like a positive quadrant in 4-dimensional space. So the differential form for this space is completely trivial. It's dx over x, dy over y, dz over z, dw over w. But now if we go to L loops, so this is L loop scattering, 4-point L loop scattering, we have 4 L variables. For each loop, we have one x, y, z, w. They are all positive, but in addition, they satisfy mutual positivity. So they satisfy some quadratic inequalities in these variables. And that's the whole definition. For each pair of these lines, of these like labels, I and j, you have some quadratic inequality. But there is, for large L, it grows like L square. It's L choose 2. So there's a huge number of quadratic inequalities. And this is a very hard mathematical problem. What people say, this is almost impossible to solve. However, there is some simplification from physics, because we definitely are getting answers. The amplitude exists, and we can calculate it, but there is something that we need from mathematics to learn how to solve these inequalities, because if we know it, then we can immediately calculate this 4-point integrand to all loop orders. So we don't know how to do it. In the last 2 slides, let me mention how we approach the problem recently. We can basically start with this very complicated problem with a lot of inequalities and do certain expansion. So instead of this space, with this large number of inequalities, we simplify the problem when we only take fewer inequalities. So of course, if the number of these mutual inequalities goes down, the space becomes simpler, and eventually it's solvable. Yeah, and without going into too much details, there is a way how to expand this one geometry as a sum of many geometries with increasing number of these inequalities. These are these pictures that we call negative geometries, just that these links correspond to negative inequalities, not positive inequalities. And we can calculate the simplest ones, which we call tree geometries. And then once we have some loops in the space of inequalities, so it's a kind of a loop in loop space, that each dot corresponds to loop momentum, and each line corresponds to inequality between these loop momenta. Then we see that the simpler the geometry is, then simpler the expression is. And here I'm really talking about the expression after integration, because once you produce the integrand in some suitable form from this geometry, you can find some differential operator which actually allows you to go from the integrand to the integrated answer. So here we are really talking directly about amplitude. So that's something that we did recently for some simpler geometries. We found the answer for the integrated amplitudes, not just for the integrand. And then we were able to resum pieces of the amplitude at each loop order. So not the full amplitude, not the full one loop, two loop, three loop, but take piece of one loop, piece of two loop, piece of three loop, piece of four loop, which correspond to simpler geometries, and resum them to all loop orders. And then the resummation to all loop orders, this is just some arbitrary approximation from the physics point of view. But the interesting thing is that once we resum, we can then expand it at strong coupling, weak coupling. It's trivial expansion, but we have a full expand also at strong coupling. And it gave a surprisingly good approximation to something called gamma cusp. It's a leading IR divergence in the amplitude. In this theory, it's just known from integrability to all loop orders. And we got surprisingly good result at strong coupling, which is something you wouldn't expect with arbitrary approximation, resumming to get anything relevant. So instead of some coefficient 2 at strong coupling, we get 8 over pi, which is close to 2. So this seems like a good approximation. It's not the full answer yet. Okay, so let me go to the summary. So in a very impressionistic way, I define the amplituhedron as a new mathematical formulation of the problem of gluons in this specific quantum field theory, especially for tree-level and loop integrand, despite recently we are able to say also something about the integrated answer in some cases. Now, the physics is here reformulated in the mathematical language, no reference with the standard notions of particles and interactions. So it's a different repackaging of the same thing. And also, by now, it's a example of a larger class of positive geometries. So Nima and his collaborators recently had work on amplitudes in phi cube theory, which seems to follow the same pattern. And there is also some work on nonlinear sigma model and other things. So the amplituhedron is a prime example, but it seems to be an example. There are more examples of this more general setup. Okay, thank you.
Thank you. So I know that
Talk about what
what's supposed to
right in the sound. Yeah, I will not talk about. Yeah, I didn't talk about that. Yeah.
So, okay. Thank you.
Yeah.
So, right,
Well, it's a very different repackaging of the problem. Yeah, but it doesn't apply to that. Yeah, let me just say, we don't know how to do it for gravity or waves or cosmology.
actually, the question is, how could we possibly pay strong because space time?
So, well, I can. So one thing which we don't know how to do, but potentially can be done, is to talk about gravity amplitudes. But these will be still amplitudes as fluctuation around the flat space-time. So take G mu nu as eta mu nu plus H mu nu and do the perturbation theory for that. So we don't know how to do it, but this might be doable. Yeah, there are many caveats because these theories are not planar and UV divergent and so on. But okay, one has to deal with that, but potentially can be done. Now, here talking about the gravitational physics, this is kind of a different part of the scattering amplitude story when you are looking or you are using the scattering amplitudes and taking the kind of classical limit of them and extracting the classical information out of the quantum scattering amplitude. There are different ways how to do it. This is one way. The other way is to using like Wilson. Yeah, different ways how to do it. But from the scattering amplitudes point of view, it's that. Yeah, but it's again, it's a perturbative expansion. So we are treating gravity perturbatively. And then the application for gravitational waves, you only keep certain pieces from the quantum amplitudes. Yeah, but again, it's not, yeah, it's very far from what I'm doing here, but the general thing about treating gravity perturbatively, so we are not in the strong field regime for that. Yeah, then, yeah, we are still doing perturbation theory at all levels here. Yeah, I did this resummation, but it was like a very specific thing where there was no non-perturbative physics, and I was able to resum it. Yeah, but it's very, very far from this. Yeah. So even people who apply to gravitational wave physics don't do what you would like. Yeah. Okay. Yeah. I don't know. We have to talk about it. Okay. Yeah. Gee.
So if we focusing mostly on the plane responsibilities, there's a possibility.
Yeah. Okay. That is the biggest challenge, the non-planar part. Actually, there are like many directions how to go from that. So even the Nima's recent story for phi cube is planar. Yeah, in a sense. So the non-planar has one big obstruction, and that's a change of it's a choice of labels, because here everything what I did here depends basically on the fact that you can choose global labels for scattering amplitudes. Yeah, it's about these momentum twisters. But even if it is not momentum twisters, some other labels that you can write the amplitude as a rational function in some labels of the whole thing. But once you go, this is possible in planar limits. If you go beyond planar limit, even if you look at individual Feynman diagrams, they have all different labels, and there is no way how to kind of line them up. Yeah. So it's not clear what are you talking about. Even before you do any geometry, it's not clear what the loop integrand means. Yeah, for that. There have been recently proposals how to do it, but they always kind of either do some restrictions, so the object is not unique, so you can get many different objects that you talk about, or it requires take all diagrams infinite number of times with all possible labels that you can label them. Yeah. So there is a problem with labels. Yeah, first. Now, maybe you can kind of not label anything and go into more abstract space and not talk about any labeling. Yeah, so that is possible. Now, one thing is that once you go to the non-planar version, even of n equals 4 superiorinals, we are losing a lot of symmetries of the theory. So it's still a conformal theory, but it doesn't have these hidden symmetries, which helped us a lot here. So, so the label problem is the most complicated one. Yeah. So from that point of view, it's actually easier to do it even in planar QCD. Yeah. So planar QCD, one has to deal with UV divergences and UV physics and so on. So that's a new thing that we don't know how to incorporate here, but possibly could be incorporated. But the non-planar is even bigger challenge. Yeah, even if n equals 4.
Possible construction like theory without getting things.
Yeah, so yeah, that's what I was just saying. So here it has a dual conformal symmetry, but from the which allows us to choose these nice variables. But kind of the main message from the existence of the symmetry is that everything is just about IR physics. So all the poles which translate into boundaries of the geometry is all about IR. So if you lose it and go to planar UCD, even planar n=1 superdiagonals, then you start to have UV physics. And at the moment, it's not clear how to geometrize the UV physics. Yeah, it's some new poles in the amplitude, new singularities, and you have to kind of transport that information into geometry. So the amplituhedron is about IR physics, but something new is needed to also incorporate the UV physics, which would be necessarily there if we go outside this theory. Also, Jonathan. Right. Yeah, it's a very good question. Yeah, because we deal just with this integrand, we don't need it. But once we integrate, we do need it, of course. Now, all the kind of ways, all the examples when we actually went after the integration, we bypassed that problem. Yeah, by doing some trick. But it's a very good question what it means in the geometry. Yeah, it's an open question. Okay, thank you.